Hello, this is second clips for the chapter 5 collected of tests for the material testing. We have discussed about the static tension, static compression already, and now we are going to discuss about the shear. Let us consider the bolt. Okay, that's we have bolt here. This bolt subjected to what? This bolt subjected to the force that's applied to this, and the bolts will resist that force by the connector here. So if we draw the free body diagram of the bolt, we will have the applied force here, and we will have also the resistant force here. If this is F, this is going to be F over 2, and this is going to be F over 2. And if we cut the bolt by this portion and this portion, and then we redraw the free body diagram of this part of the bolt, what we have is the force F. The force F must be resisted actually by some kind of resistance occur on this portion also, and we know that this one going to be the shear, and this shear going to be equal to F divided by 2. So this condition is the double shear. We will test this kind of bolt in our lab to study the tau ultimate, okay, or ultimate shear stress of copper, okay, of copper, of brass, and of aluminum. And we also will going to study the shear strength of the wood. We're going to put wood into the machine and fix it around here and put the force into the wood here. And then what happens is the force will be shear, and it's going to have a crack in this direction. And what we have is this portion of the wood, okay, will subjected to the shear force here. Okay, so if the force is F, so the shear force is going to be F. This one we call it single shear. So we're going to test our specimen, both double shear for metal and single shear for wood parallel to gain in this material testing. And okay, what I mentioned, I just past mentioned, we have the shear test and we have the direct shear test. The direct shear test can separate into single shear and also double shear, okay. But we have another shear that's civil engineer also use a lot. Is the shear is torsional shear. For the mechanical engineer, they use the torsional shear in design of the shaft of the structure. If you going under the truck, and you may see the structural member that's linked between the engine and the rear wheel transmission. That's called the shaft. That's going to transmit the engine power to spin the wheel to drive the car. In civil engineering, we also use the torsion when we investigate the soil layer. We need to have the auger. Okay, the auger is some kind of a shaft with the special design, so we can dig the soil. It could be the shaft like this. Okay, it has some kind of spiral still here. Okay, when you twist this, the auger will dig up the soil, and then you can investigate the soil layer. Also for the piling, like the ball piling, you can boring the soil, and you put the reinforce into the boring, and then you put the concrete into it, that's you going to produce the pile also. Okay, so this is going to be the leg shear, and the first one going to be about the double shear, and the second going to about the single shear that I just mentioned before. And for the double shear, so the equation is going to be half of the force divided by A, and for single shear, the force, the applied force will divide directly by A. For example, for this one, if the force is P, the force this here going to be P, so the shear stress V over here is P, and the tau going to be this equation. For this one, if this is P, okay, the force here going to be P over 2 and P over 2. Okay, and then the shear stress here going to be this equation. And thus I mentioned about the auger that you use to investigate the soil or rock layer underground, and you have this drilling. Okay, you have this kind of twisting, so you can drill the soil out, and you may investigate the layer of the soil later. An example of power shaft that transmits torque from the machine or the machine parts is also subjected to the shear force due to the torque. Torsional shear is kind of uphill shear. Okay, when you twist this specimen, before this you have this square specimen. When you apply the torsion here, the material gonna resist the torsion by the shear stress, and shear stress is going to be T and time what, time the what's so called the what's this one is R, T_R over J. J is going to be polar moment of inertia. Okay, and for the circular section in like this, for the shaft, the J is going to equal to I sub x plus I sub y. The y is moment of inertia. Okay, and the J is called polar moment of inertia. And since they are equal, so the J can be 2I. Okay, and J usually pi r power 4 divided by 2. Okay, because it's 2 times of the I, and also it's going to be pi d power 4 divided by 32. And then when we have the shear stress there, we also have the other shear stress that occur on this element also. Okay, and then when you start by this line, after twisting, this line just change into this one. Okay, and then what we have, if you still measure this with respect to the reference lines that's measured across this, you will get this as a shear strain. Okay, and also if you reference the first position by this less line, and when it's twist, it's going to twist into this dashed line, and you have this for the phi. This is the angle of twist. Okay, you can measure it, and under this you may have what, you may have the movement of this line, and by the length this of L, this distance can be gamma L, and also if this is phi and this is R, it's going equal to R phi, and then you may have phi equal to, sorry, you may have the gamma, the shear strain. Okay, not the phi, the shear strain, because you're going to find the shear strain. Shear strain equal to the angle of twist times R and divided by L. This is the L. Okay, so this time you can compute the stress basis on this, because you know the torsion, you know the R, and you know the polar moment of inertia. And you also can compute the shear strain. This is going to be shear strain. Okay, the shear strain going to compute by angle twist time R divided by L. So you have the equation. That's finally you can produce the shear stress and shear strain. And by doing the laboratory number 4, so you will have a chance to do the torsion test of the steel and torsion test of the cast iron. And you may see the behavior of the steel different from the cast iron under torsion. So you get the photograph, you got the stress strain diagram, and from the stress strain diagram that you have, there are some important points that you should be considered. The first one is G. G is the shear modulus of elasticity. Actually, you can compute G from E divided by 2 times 1 plus mu. Okay, they are relationship if you know the modulus of elasticity and mu or Poisson ratio of the material. And you also need to find this. This usually to be the shear strength of the material. Okay, is the shear of a proportional limit. And you also can determine the tau allowable by tau sub PL divided by factor of safety. Or many times it said tau sub PL equal to tau sub Y, which is the yielding shear stress. And then you can determine the tau allowable easily. And the other, you're going to determine the ultimate shearing stress and the fracture shearing stress. But very important, most of the time we set the tau sub PL equal to tau sub Y. Okay, and you can design this shaft based on these material properties. And limitation of the test, there are some limitations, especially from the direct shear test. From the direct shear test, since you put the timber, okay, and then you shear it directly, what you have, you get the approximate shear strength. Because of what? Because when you put the force into the specimen, okay, and you may fix around here, but anyway, there is a crack. The crack is going to occur usually in this portion. It's very hard to take a look at this portion. Okay, and then we also have the shear that occur over here. So there is some eccentricity about here that cause some bending stress on the material. Okay, and it may have some effect on the obtained shear stress. Also, there is some friction of the contact surface of the specimen. And for example, when you do the test of the steel, you have the plate like this, and you also have the plate like this. And then you fix these two to the bottom plate. Okay, and then you have this. And then you put the specimen, okay, cross them like this. That is going to be a specimen, and then you pull this. So there is some friction occur in this point, okay, and that may cause some deviation of the result from the direct shear test. The second, this test cannot provide other mechanical property such as the shear modulus, but we can have the shear modulus of elasticity by doing the torsional shear test. Okay, that means direct shear test gonna give us very simple shear strength. Usually is the tau ultimate, the failure of the shear stress and the failure of the specimen. For the torsion test, have a limitation. It cannot provide the shear strength of brittle material. Why? Because brittle material fail by tensile strength. I will mention this about the failure of the cast iron. Okay, later cast iron fail by tension. So by doing this, we didn't get the shearing strength of the cast iron, but we get the tensile strength of the cast iron. We have two labs. One is the laboratory number 10, the direct shear that we have for this one. No, it's not correct. It's going to be brace. Okay, that's going to be brace. This is the brace, and the copper is have the red like this, and the aluminum. Okay, and we put this specimen into the testing machine in the form of double shear, and then we get the strength of this material. And another one, we do the shearing test of wood parallel to grain. Okay, we have the wood have to put into the steel cage that's going to fix this part of the wood into it. Okay, when you shear this one, what we have is the failure plane is going to be like this, and this is going to be in the form of single shear. Okay, and the crack will be occur allow here and allow here. Okay, the torsion test, the specimen supposed to put into this. What we have this one is the steel. This one for the cast iron. We put them into this, and then we twist this one, and then we measure over here for the angle of twist by reading this indicator, and you also get the torsion from this torsional measuring machine, and then again you can compute for the tau, for the tau, and also for the shear strain, and then you can plot the shear strain diagram with this to be the tau supply. And what happened is specimen for torsion is not large enough, so the measuring of the shear strain by measuring the angle twist may have some error. Another one is the specimen is not long enough. Okay, so it may have some stress concentration occur at the grips of the specimen when we do the test. And the third one, the specimen supposed to be thin wall. If we like to determine the shear strength of the material properly, the ratio of the thin wall going to be 10 to 12. That means what? That means it's going to be the specimen with this one, and the diameter to the T. This is going to be the diameter and the D. Okay, and this is going to be the T. The ratio of D over T supposed to be larger than 10, and it's going to be supposed to be between 10 and 12. Sorry, on this it's going to be 10 less than this, and this one could be 12. Okay, this one. Okay, and 12. It's going to be in this proportion to get a proper strength. Why it's going to be this? Because the stress that occur on the thin wall is going to have some kind of stress here. Okay, if it's thin enough, the stress here gonna be nearly equal, and the measurement going to be correct. But if the specimen is like a solid segment, what we have is the stress occur in this section will not be uniform. It's going to be something like triangular like this. So we need to have the thin wall specimen to measure the shear strength. And we have for totally 3 laboratory related to the shear test. One is the torsion. Okay, torsion of the steel and the cast iron. We will discuss this later. And the other one is direct shear. Okay, that is going to be the double shear. It's going to be the brass, copper, and aluminum. Okay, and the third one is just stress of wood parallel to grain. And the failure of the specimen. Let's see. The steel, when it's subjected to torsion, the failure of the plane is going to be smooth like this. So when the steel subjected to the tow, the failure also due to the tow. Okay, and then it's going to be 90 degree parallel to the axis of the specimen. Okay, for the brittle material, the failure gonna be in 45 degree like this. So brittle material subjected to the shear stress, but it's failed by normal stress, the tensile stress at 45 degree. And this is what explained for the ductile material. Okay, the failure plane is going to be in this way. For the brittle material, the failure going to be in this way. It's going to caused by the tension. This one causes by the shear stress. Okay, and when we compare the results from the tension test and torsion test, what we have is for the steel, the steel always fail by the shear stress. Okay, by shear stress. However, for the tension, is caused by necking. Okay, but for the torsion, is caused by the direct shear. Okay, the shear. And when we consider the cast iron also fail both from normal in tension or in torsion. However, this is due to the separation, okay, of the plane of the grain of the material, and this one due to the tension stress that cause 45 degree crack. So the cause of failure, the steel due to the shear stress, the cast iron due to the more stress. And this is going to be related to the failure criteria that we study in the master degree also. However, the plane of crack are in opposite. Okay, if you put it into picture, you're going to have these 4 pictures in comparison, and please separate them clearly. What is the cause of the failure of the steel? What is the cause of the failure of the cast iron? Okay, that is the end of the shear, and we are going to move to the next part. Is 5.4. 5.4, we're talking about the bending. Okay, when we're talking about bending, you may recall that means it's going to be the beam. We have the beam and our beam subjected to the force. Let's say this is P. You may get this reaction, and it's going to be P over half and P over half. if this one is L/2 and L/2. Okay, this kind of test is called three-point loading test. What we like, what we have like to have this one, we measure what? We measure the P, and we also measure the deflection of this. Okay, and what we have from this is the shear diagram for this. This one going to be plus P/2. This is minus P/2, and also the moment diagram. Okay, and the maximum moment here, that's going to be under the load. It's going to be P. This is L/2, right? P/2 times L/2 is going to be PL/4. Okay, and then when we test this, we interested in what? Interested in fractional modulus of elasticity. Okay, we will be talking about this later. We also consider the modulus of rupture. Modulus of rupture is the stress of failure. It's not the modulus, it's a stress of failure under friction. That is usually for the brittle material. Okay, and we have also different type of this. Consider this one. We push the force here, and what happened is what this force separate into this one and this one. If this is P, this is a P.5, and this also P.5, and then we have the reaction here and reaction here. Reaction going to be P.5 and P.5. What we have here is the shear force diagram in the shape like this, and we also have the moment diagram in the shape like this, and our shear gonna be P/2 and minus P/2 here, and the moment, since this one is L/3, and L/3, so the maximum moment going to be P/2 times L/3. That is PL/6. The good thing here is you can see in this portion there is no shear. So if you study the failure of the material due to the pure bending, this formation is good. Okay, but if not, the setting up of T-point loading is going to be easier. This kind of setting, we call it 4-point loading test. Okay, this is another test. It's kind of a little bit harder to set up. So in the lab, we are only interested in the 3-point loading test. Okay. It should be noted that the bending test is usually used to find the tensile stress of brittle material. It's really useful to find tensile stress because the brittle material usually is hard to catch the specimen during the tension test. So it's better to this catch it with clipping. You have the clipping problem at the end of specimen. So we use this fractional test for the brittle material. And like I mentioned, okay, this is 3-point and 4-point loading. And any kind of loading test, we have this equation to determine the fractional stress. Okay, and it's only used in the linear elastic. Okay, when you bend the specimen, okay, the upper part gonna be in compression, the lower part gonna be in tension. Okay, if you design the reinforced concrete beam, most of the time you put the steel in this tension part to taking care of the tension in the beam, and the stress that occur here is going to be compression on the top, and it's going to be tension on the bottom like this. And since this the top going to be in contraction, the bottom is going to be elongation, and there is a point between top and bottom. It has no deformation. We call this is as the neutral plane. Okay, no contraction and no tension. The stress here is 0. And if you put it in the model, okay, the beam have the linear elastic behavior under the pilot. The strain going to be have linear distribution like this, and also the stress going to have the linear distribution like this. And then we have the equation that's compute the fractional stress sigma equal to m moment, okay, and y is the distance that you measure from the neutral axis up to the interesting point. And then you may see that since this one is large, so this one will have the maximum moment of m, and then c max over moment of inertia. So the compressive stress going to be larger than the tensile stress for this section. And the moment of inertia, you know it, right? Because if you have the rectangular section like this, it have B and this is H, the moment of inertia about this I is going to be B H cubed over 12. You can compute it easily. Okay, and sigma max is going to be defined by that. And the strain can be computed by the stress-strain relationship. Okay, now, what is the maximum stress for beam with brittle material? And we have linear elastic to failure. The beam is going to have the behavior like this. This is P, this is delta, and then it's going to have the behavior like this and fail here. So this is the linear elastic. Okay, modulus of rupture. Modulus of rupture is the stress of the failure of the material can be computed by this equation. How we can get this equation? This is sigma equal to m y over I. Okay, thinking about this, I equal to what? T times 2c cubed over 12. So it's going to be 2 power 3 is 8 t and c cubed by 12. So this is going to be 2 over 3 tc cubed. Okay, and the moment due to the T point loading is going to be, we know that P L over 4. Okay, and then the Y you measure up, measure down for this is going to be equal to C. Okay, and then you divide it by this one, 2TC power T cube, 2TC power T or cube, and then it's going to times 3 here. So what we have is this cut, this is going to be 2. So we're going to have 3 PL, this is going to be 3 PL divided by 4 times 2 is 8 TC square. Okay, you got the fractional, you got the modulus of rupture by this equation. You can prove it easily, and many times in the examination I ask you to prove this step by step to get the equation that we can use to determine the modulus of rupture of the brittle material. Okay, it's very useful to determine the tensile strength of the brittle material. Okay, I also assign you to go back and review your static to draw the shear diagram and moment diagram of the 3-point loading and 4-point loading. And I should note that in this region of 4-point loading is important because it's the stage of pure bending, which is good if you prefer to study the behavior of the material only in the pure bending. That will be in accordance with the fractional theory. And then you're going to determine the fractional yielding strength Okay, and as I mentioned, from this test you will get the graph of the load and the graph of the central deflection, and each graph represents the behavior of the steel. Okay, let us consider the first two, and the equation that's used to determine the modulus of rupture also used to determine the yield strength of the ductile material such as steel. Okay, this is the graph of the steel. We're going to use the 0.5% offset according to the ASTM. Okay, what it means is we're going to determine the 0.5 millimeter. This is in meter, and this is going to be 1 meter, 2 meter, 3 meter. So 0.5 is going to be here, and then you push, you draw the line parallel to the first part. That means this one you draw this line parallel to this one, and when it cut this point, you get the P offset, and then you put the P offset back into this equation. You determine the yielding stress of this material, and you also can check for the second one, but this time you got to draw the line that's parallel to the second graph, and see you get the P offset very close to the first one. Okay, but two graphs are a little bit different from to determine the E. Okay, next we also can determine the E. What the E? We can determine the modulus of elasticity of the material of the beam via test. What we have is, if we do the 3-point loading test, okay, under the application of the force, the beam will deflect, and we have the V max over here equal to PL cube over 48 EI, and you can see this is the delta P, and this is the delta, and you may find the slope by delta P by delta theta. So by doing this, you may put P over V. You put the V down, okay, the P, and then you move 48 EI up, okay, this one up, and divided by L power 3. So actually the K can be related by this equation, and if you know K, we can determine the E. Okay, fractional modulus of elasticity of 3-point loading test can be determined by this. As I do before, you rearrange the equation like this, and then you get the K equal to 48 EI divided L cubed. Okay, by doing this, you got this equation. If you don't know it, you can open your textbook and find it easily, and then you get the K of this material of the beam easily. Okay, there are some limitations of the test results of static fractional test. First, the deflection of the beam may not produce by the moment only. Okay, if the beam is the deep beam. What is the deep beam? Is have the ratio of L over D divided by 10. That means the beam have the shape like this. For example, is have the ratio of L. This one is the L, and this one is the D. Okay, this is less than 10. So when it's subjected to the force, what happened is there are some changing in the deformation here, like this. There are some what so-called shear deformation. Okay, when it's have shear deformation, the deflection will include both bending and shear, and the result may not correct. So our beam to be considered must be long enough. And second, in determining the proportional stress of the beam, the top and bottom of surface of the beam subjected to maximum stress. That means for this, what is going to be on the top? The top going to be in tension, right? Okay, the bottom going to be in compression, something like this. Okay, it may have starting point of the yielding. Therefore, the yielding, the start. Sorry, the proportional stress start at this proportion. Only the top and the bottom reach the proportion, but the inside won't. So the value that's computed by this fractional stress is just approximate value. Okay, because it won't occur at the same time, unlike for the tension. Okay, this is another picture showing you only some part has the yielding and the other won't. For the specimen, we gonna design the specimen clearly. First one, if we like to avoid shear failure maybe occur as a crack, okay, at this portion of the beam, because under the force, this portion gonna have the V max, okay, and that means to prevent from the crack at the end, you got to have the ratio of L over D between larger than 10 or 12. Usually we use it larger than 10, depending on the type of material, shape of structure, and applied force. Okay, and to avoid the buckling, if you bend the ruler, projector ruler, you can see the lateral buckling in the shape of this. If you have the beam, very thin beam, and you bend it, okay, you're going to get the beam with some kind of what's so-called lateral buckling in the form of this like bull-like. Okay, to prevent it, you're going to have the ratio of D over B larger than 15. So that means your specimen supposed to be thick enough. Okay. For the testing machine and testing procedure, we have 3 types of fractional tests in our study. We also do the fractional test of the brick. Okay, sometimes brick also subjected to bending. For example, the wind, when it's subject to the wall, when the wall subjected to wind, okay, the brick also in fracture. And we have the lab number 8. On lab number 8, we do the fractional testing of the wood. Okay, we also do the long wood and short wood. Long wood usually fail by Mmax, and short wood may fail by Vmax. And also we do the fractional tests of steel. Okay, fractional test of steel is going to produce the yielding. Okay, or it's called plastic hinge. And for the cast iron, the beam gonna fail abruptly for the cast iron. Okay, and when the test, you got to be careful when you test the cast iron. Okay, I recommend you to tight the cast iron specimen with the testing machine. When it's broken into 2 pieces, it won't fall down to hit your foot. And something should be noted on this. First one, during the test, we should notice and record the following: the type of specimen, the defect of the specimen is very important to defect specimen, the dimension of specimen, the loading of specimen, and some special type of failure. of the specimen. Second, for the finding the fractional elastic modulus E, that's going to be defined from the slope K. Okay, the E that we have will be very close to the tension test and compression test. And let's note that this fractional test or bending test is very good for the brittle material, right? And the third, to obtain the proportional limit. This one may be a little bit larger than this one obtained from the tension test or compression test. As I mentioned before, since the distribution of the stress of the beam like this, so when it's reached the proportional limit or yielding, it won't reach that point simultaneously. So only part of it reach that stress. So that means we measure only that behavior, not the whole section. For the rupture is the failure of the brittle materials, such as when you put the concrete into fracture, concrete will crack easily. Okay, there is the research. Yes, crack easily. There is the research that we put like a glass fiber or the steel fiber to the concrete, so that will improve the tensile strength of the concrete. Okay, the failure of the concrete or the brittle material initiate at the micro crack in tension surface, and the crack expand rapidly due to the tensile strength of material until the beam cross section cannot take the load, and the failure occur immediately. Okay, and the failure of the timber beam, we also test the timber. There is different kind of failure of timber. The first one is of kind of a simple tension at the bottom, because this portion is in tension. Okay, this fail like this. This portion also in tension. This portion in tension. This is maybe due to the grain. Okay, have some kind of special grain direction, so the failure occur there, and the D like this. The compression also sometimes we observe it, but mostly we observe the tension. And the third, lateral deflection. We can prevent lateral deflection by putting a larger width section for the specimen. And the horizontal shear. This occur only for the short beam. We can design the experiment so that the beam fail by horizontal shear, and you can go to the book of Hippler and find why the beam fail like this. Because of what? Because of the short beam going to have large V max equal to P over 2. So when it's subjected to the large force, the distribution of the shear stress is going to look like this. So the maximum occur at near the middle of the beam. So the crack occur here. Okay, going back to read the textbook about this, and the compression, and that is going to occur. This one, the 5, occur due to the stress concentration of the applied force. And I will have an example to show you for this. Okay, this is the one that occur, but it's occur later than what? Later than in tension. So this example have two kind of failure. One is due to the clutching at the loading point, as I just circled the red one. But the other one occur like this. Which picture? It's going to be picture number 1, picture number C. Okay. And also, we found the crack at the end of this beam due to the shear stress okay, and we didn't find often. Each year I found is only one or two. Okay, and the top is a picture of our testing setup. We put the beam between the support, and then we put this. And I should mention that at the loading point, you got to put the steel plate here, okay, to distribute the force and prevent the failure over here. The yielding is a progressive failure of the specimen for the steel, for the aluminum, okay, is formed by the stress that occur on the section. When the stress, the maximum stress, reach the sigma sub y, okay, the stress start to produce the behavior of the hinge at the loading point, and you can see from the test the plastic moment, okay, will produce this kind of behavior, and the material at this section will behave plastically and form the hinge over here. And what happened later, that the deformation of the beam will increase rapidly under the small increment of the force. Okay, the factor that affect the fractional tests, there are many of them. The first one, loading type. Okay, for fractional test with the simple beam, you know simple beam, right? Simple beam is the beam that in the form of 3-point loading. Simple beam is going to be like this. The modulus of rupture, the failure stress is occur in the beam at the midspan. Yeah, sure, that's going to occur at this point. At this point, because it's going to have the maximum moment, it's going to be approximately 7% larger than that's calculate value from the rupture section. The fractional test for cantilever beam, you know cantilever beam, right? The cantilever beam is going to be the beam like this. We didn't test this in cantilever beam. I never. Okay, it's going to put the force here. What we have is the tensile strength. Tensile strength usually is the yielding stress is larger than obtained from the p-point loading. That is because of what? Because the failure of this occur at the support, and this is fixed. Okay, when this is fixed, it can take larger stress, so it's produced or the force that caused the failure of the cantilever is going to be larger than those from the T-point loading. Specimen dimension, big specimen dimension. When the span is shorter, what we have is from the fractional test of the concrete beam and from the cast iron beam. Okay, when the beam is shorter beam, the modulus of rupture going to get higher. That is a notice for the test. Okay, shape of the beam, we have the I section. I section show the higher failure load than the rectangular cross section. Okay, just use this for some notice. You may have a chance to test the I section or rectangular section when you work in the field. Okay, the size, larger size may have a lot of defect. Okay, so the fractional strength going to be decreased due to the larger size going to have more defect. Okay, more defect than the smaller section. Stability, build up beam with the thin wall such as the I-beam, when you test it, okay, it's going to have some instability problem. But this one, okay, you have the lift of the wall of the thin like this, okay. When you push it, the top portion of the beam that is subject to compression may have some kind of warping here. There's some kind of that instability that occur due to the buckling of the thin plate. Okay, that is going to be in compression. For the wide flank beam, have the width to thickness ratio less than 15. That is going to be thin. Okay, thin wall section. This beam will got warping. This is the warping. What I'm saying, the warping of the section is a local flank warping. That is going to be occur in the compression zone. It won't occur in the tension because tension will try to elongate the flank. However, the compression going to contact the flank. When you contact the flank can warp it easily. And also they have a lateral buckling. Okay, before this, the element stress here. Okay, after the application of the force, it may have the lateral buckling. That is going to have this one, this size wave. And also the combination of lateral and torsional buckling. That's mean what? That's mean before this, you have the beam, okay, lay here under the force, and then your beam move laterally. This is gonna call laterally, and also it's twist. It's twist. That means it's twist from the vertical like this. This is called the torsion. This is twisting. And there are some kind of very thin web. For very thin web, you know web, right? Web is L. Okay, very thin web. If the web is very thin, under the force, web can be rippled like this. Okay, this kind of the beam for the airplane more than the kind of the beam for the civil engineer, and just make you the notice on this. And also this is what I did in the lab. I did some mistake because I didn't put the steel plate to distribute the force here, so it has some kind of stress concentration failure here, okay, due to very high concentrated load. Okay, and it's also causing the web to be warping like this, also due to this kind of local failure of the beam. Okay, the last one we're going to talking about the fatigue. In structure, if you have the bridge, you consider the bridge, right? What happened the bridge? If you have the bridge usually subjected to what? To the vehicle load. And what the vehicle load? Vehicle load is a kind of moving load. Okay, moving load. When the bridge subjected to moving load, what happens is the bridge will deflect a lot when the truck come to the bridge. Oops, sorry. It's effect like this. Okay, it's going to be in tension on the bottom. Okay, and when the truck passes, it's just going back. Okay, what happened is the force that's applied to the bottom part of this start by 0, for example. Okay, and then when the truck comes, the stress just going up in tension, and maximum. And then when the tug pass by, the stress just drop down to 0. So this happens every time when the tug pass. So that means the bridge is a kind of a structure that is subjected to life load that change inside that magnitude with respect to the time, or we call this one as the cyclic loading. There are many patterns of cyclic loading. This is going to be tension compression. This is going to be only in tension, and this is going to be a lot in tension and small in compression. So it depends on the type of structure you consider. Okay, and for fatigue, when the metal structure usually the ductile material, okay, is gonna have progressive failure. But when it's subject with the stress less than yielding stress, that means it's still in the linear elastic. But when it's subjected to this stress for a continuous period of time, okay, the material just get fatigued and the failure occur as the abrupt failure. That is a kind of brittle failure due to the fatigue. This kind of important behavior that we need to be very careful on it. Okay, and especially when we decide the steel bridge, or since the steel bridge also subjected to the cyclic loading. Okay, another one that's popular in the recent year is the wind turbine. The wind turbine also subjected to fatigue because it's going to have very large stress near this end of the turbine. Okay, and the force acting on it is the moving force due to the wind. So you got to be very careful on this. Some nomenclature that you should know about the fatigues. The first one is the mean stress. Mean stress is the mean average stress. So you just put the sigma max plus sigma min divided by 2. And also this is sigma max, and this is sigma min. Okay, and this is sigma max in tension, sigma min in compression. So sigma mean is sigma max plus sigma min divided by 2. So stress amplitude. The stress amplitude is the total length of the stress and divided by 2. So that is the amplitude. And the stress length is sigma max divided sigma min. So the sigma amplitude is just the sigma length divided by 2. And if we consider some example, let's check up the wing of the airplane when it's maybe subjected to the wind during the flying. When we have sigma max of 10 and sigma min of -2, we can determine sigma m. Okay, the sigma m is going to be what? 10 plus -2 is going to be 8 divided by 4, so it's going to be 4 megapascal here. Okay, and if we like to determine the order, just stress amplitude. It's going to be what? Sigma max minus, let's say minus sigma min divided by 2. So it's going to, well, divided by 2 is 6 megapascal. And stress length is going to be the total length of sigma max minus sigma min is 12 megapascal. Okay, and when we do the test in the lab, okay, we will put the specimen. Put the specimen into the machine, and we put this portion into the motor to spin it up. And what we have is we're going to push the force up here, okay, and the force P gonna produce stress 1 if it's large, is small, let's say small, it's going to produce very small deformation like this. Okay, and if you increase this to sigma 2, S2, S3, S4, okay, you're going to get the stress that's corresponding to P1, P2, PT, and P4. And if you spin this structural member by the test, the S1 may fail as N1. If this one is small, though, the S1 is going to be large. Okay, is S1. That means if the stress is small, for example, if your stress is just like this, you're going to get 1 million. And if your stress is large, N is going to be small. That means if your stress is 700, okay, your N is going to be, that is log scale. This is going to log scale. Okay, that is going to be like 300,000. Okay, and that is going to be the graph we call the SN curve. Okay, that's obtained from the fatigue test. Like I mentioned, it's the relationship between the stress amplitude with the N is cycle to failure. So we call it SN curve. S is the vertical axis, and N is going to be the horizontal axis. Okay, it's constant, and then the horizontal axis put in logarithmic scale. It's going to put in logarithmic scale. Okay, and then what we have is fatigue strength. Fatigue strength is the relationship between S and N. That is the stress that the material can resist from a given cyclic loading. Okay, cyclic loading. For example, if you like to have the material in the structure that can take 10 power 5, that is 100,000. So the stress is going to be 580. And if you like to take more cyclic loading, the stress reduce to like 460. Okay, and there is the stress that the structure can take without the failure. Okay, that is the endurance limit. Below this stress of 414, okay, the material can take the stress infinitely. And for some structure, like I said, it has the endurance limit, which is the stress below this material can have the infinite life it can take. And luckily, our steel, for example, that has the sigma sub u of 820, and you may have the endurance limit of 414. That is about half. Okay, about half, or is a length of 0.5 to 0.6. Usually, the sigma sub e will be approximately 0.4 sigma sub u to 0.5 sigma sub u. In civil engineering, our steel, such as the Fe steel, we have what? We have the yielding of 2,400, and we determine the sigma allowable by divided by 2. So most of the time our allowable stress that's used to decide the structure is 1,200 kilogram per square centimeter. And if we consider the endurance limit to be like 50% or 0.5 of sigma sub u, so the endurance limit of the steel can be 2,000 kc. So our sigma allowable a lot lower than the endurance limit. So most of civil engineering structure, they won't fail by the endurance limit due to the coding specification that I just mentioned. before. Okay, and however, you got to be very careful when you have the welding. When you weld the beam usually very long. Okay, it's maybe have a piece of 8 meter, and then you weld it with another 2 meter. And this welding, if the welder are very good, when they have the special way to cool the welding, that's going to make the welding to be homogeneous with the steel of the beam. But if the welder is bad, sometimes they just pour the water into this welding and cause the crack of the steel over here, and that is very prone to fatigue. Okay, so beware about quality of construction when we talking about building the steel bridge by the welding. Okay, so most of the time our structural steel will not fail by fatigue due to the factor of safety of 2. Okay, and we have some non-ferrous metal such as the aluminum. The aluminum has no endurance limit. To do this, we got to set up possible endurance limit by taking the state value corresponding to some specific value that depend on the function and importance of the structure. Okay, you will set the band. If your structure can take very large number of cyclic load, for example, if your structure gonna take like this one maybe like a 8 times 10 power 7, so you decide this with the stress here, that's maybe about 160. If your structure gonna take like only a million cycle along its life, such as some part of the airplane, you can design it with a higher stress of 220. So it depends on you, depend on what you are going to use. The structure is subject to a lot of loading, so the stress is low. It is subject to a limited number of cycle, so the stress can be higher. And by doing that, don't forget to inspect the structure frequently. Okay, the limitation of the test. In practice, the structure is not subjected to constant cyclic load as we use in the test. So when you use the testing result, okay, you need to be very careful, especially for small specimen. Okay, that's maybe inaccurate. Using the result must be very careful for the real world application. And the second, fatigue is not used in quality control tests. I mean, the steel company usually didn't do fatigue tests for the steel. So if we need to do, you got to do it by yourself. The testing machine and testing procedure, we have only one test for the laboratory machine, okay, fatigue test of aluminum, and just take a look at this laboratory manual. It should be noted that the fatigue test to find endurance limit require a lot of number of tests, and it's going to be very expensive. Okay, the test is usually start with a high stress, so we will know the failure very quick. It's going to reduce, okay, times, okay, and we supposed to test to 3 to 5 specimen for a given state length. For example, if you test the specimen for very high 600 megapascal, you should test 3 to 5 specimen. And also, if you like to go down like a 500 megapascal, you still test TO5. That means you're going to test a lot of specimen. Okay. The fatigue test panning, you got to consider the type of loading variation. Usually the load is inside function, as one we have in our lab. The mean stress computed by this equation. Our testing state in general first specimen set should be tested with maximum stress. Usually it's going to be like 10% for the next. Let's say if you have the specimen with the stress of sigma sub u of 400 megapascal, we may start by 360. Okay, and then the next one start 320 and 280 and 240, something like this, by 10% until you get the endurance limit, which usually is about half to 100. That means you're going to test is 1, 2, 3, 4, 5, and 6 set. Okay, 6 set of tests, and each set could contain about 3 to 5. That means if it's 5, you're going to test it for 30. If it's 3, you're going to test for 18. And the frequency of the test, the STM E466 set is going to be 170 Hertz. That is going to be 170 cycle per second. If you're going to test for 1.7 million times, so you're going to test it for 10,000 seconds, and that is going to test for what? 10,000 is going to be divided by 3,600 seconds per hour. So you will test about 2.78 hours. That means about 2.78 hours for each specimen. Okay, if you test like 3 specimens, you're going to spend a whole day testing this material. And okay, that is the end of second part of chapter 6. We study the characteristics of tests, and the first video clips we talking about the tension test and compression tests, which is very important, which are very important to our civil engineering work, because the tension test usually test for the steel, structural steel, the reinforcement steel, the pre-stressed steel, and the compression are important because we test for the concrete, we test for the brick, and then we move to the shear test. We didn't do much for the shear test because most of our structure, unlike in the mechanical engineering, didn't subject to the torsion such as the shaft. And then we discuss about the bending. We have some structure that's subject to bending in our civil application, such as the beam. So it's kind of important also. And the last one for the fatigue test, that's kind of a special test. To be a special engineer, to be better than the other people, you got to know something special. Not much university in Thailand has a fatigue test like us at the SUT. So if you have that lab, I like you guys to enjoy it, learning it to make you special in some cases. Okay, that is the end of chapter 5, and we will move to the chapter 6 for the next clip. Okay, bye for now.